everybody in the meeting room has already some basic knowledge on optimization. So I will just recall so the most general definition of a combinatorial optimization problem. So we are given a combinatorial search space and optimization objective over this search space. So the basic objective, the basic goal of the problem is to identify among all the possible solutions in the search space, the best solution. So the best solution may be that one, maybe the one with the minimum cost or with the maximum cost. So according to whether we want to minimize or maximize. So combinatorial optimization is computationally intractable, very difficult in the general case, because the number of candidate solutions in the search space often grows exponentially with the size of the problem we consider. So if we make a general classification of existing solution approaches, we may classify these methods into three large families. So first, the exact methods that can find the optimal solutions. To do this, the methods will try to check intelligently, of course, or implicitly, all candidate solutions in the search space to find the optimal solution, so the best solution. Of course, in many cases, for NP hard problems, exact methods will have a exponential time complexity. So another class of methods is approximation methods. So this kind of methods can guarantee the solution quality. So we know when I find a solution, how far this solution compared to the optimum solution. So we have this kind of guarantee. So the third kind of methods is, of course, heuristic or meta-heuristic methods, which are typically used to find suboptimal solutions of a problem for which exact methods cannot be applied. So if we have a problem where we can use exact methods to find the optimal solutions, then there's no need to apply any meta-heuristic. There's no reason in any case to use a meta-heuristic method. So we use these kind of methods because we have trouble with traditional exact methods because the problem is too large or the problem is too complicated. So checking all the solutions, so it's impossible. So in this case, we have no other choice, in fact, to apply a meta-heuristic to find a suboptimal solution. So in our case, we will focus on these kind of methods. Okay. Before presenting the case studies, I will first recall the two problems we will use. So the first one is a graph coloring problem. So in graph theory, there are many coloring problems. So the most popular one is the graph K coloring and the graph coloring problem. So here we will consider basically the graph K coloring problem, which is defined by a given graph, okay, and also by K different colors. So these two entries are given. So we are given a graph. We are given also K available colors. So the K coloring problem is just to use these colors to color the vertex of the graph in such a way that two adjacent nodes cannot be colored with the same color. So this constraint is what we call a coloring constraint. So a Lego coloring must verify this coloring constraint. Two adjacent nodes cannot be colored by the same color. So the question is that given the graph, given the colors, is it possible to color the vertex with these K colors? Okay, so this is a K graph coloring problem. As you note, the graph K coloring problem is not really optimization problem because there's no optimization objective. Okay, but in our case, we will I will explain this later. We will transform artificially this problem. In fact, this is a CSP. This is a constraint satisfaction problem. So we will consider this CSP problem as a optimization problem. So I will explain this point later. So here, if we the answer to the question is yes, then of course we want to find a legal coloring with these colors. You may notice that this coloring problem is a grouping problem. Is a grouping problem in the sense that a coloring, so a legal coloring or an illegal coloring, in fact, is a partition, is a kind of partition of the nose into different color classes. So here in our example, we have a very small graph with 5 nodes. Okay, so we have a legal coloring with 3 colors. This coloring, these 3 coloring, in fact, can be considered as a partition of the nodes A, B, C, D, E into 3 color classes. Okay, so it's the same. So in each color classes, we have all the nodes receiving the same color. Now I ask you a question. So in our case, we have a coloring. So we have these 3 color classes. So we have a blue color classes, we have a yellow one and a red one. Now I ask you a question. Is it the colors, I mean, blue, yellow, red, these colors, are they really important or not here? Are these colors are important or not? So if you think about it, the answer is no. The answer is no, because if I exchange, for example, these colors, so this color class instead to have the blue one, if I change these 2 colors, in fact, we have exactly the same solution, the same coloring. Okay, so in this problem, in fact, the color of each color class is not important. Of course, in some other color, in other color graph coloring problem, the color itself is important. Okay, so I insist on this point because later we will somewhere we will use this feature. Okay, so of course this problem is very known and have many applications. Okay, so it's of course an NP-hard problem. So a second one is a quadratic assignment problem, which is also very popular, very well studied in operational research and computer science. So here we are given n facilities and n locations from between each pair of facilities, we have a flow. Okay, and of course between 2 locations we have also a distance. So the question is how to locate, how to assign the facility to the locations. So when we do this location, when we do this assignment, we want to minimize a quadratic function, which is here. So this is a very popular NP-hard problem, which also has many practical applications. This problem, of course, is very difficult. For example, non-exact algorithm can be applied only to problem instances with around 40 locations. So for larger problem, we have no choice to apply heuristic methods. Okay. So in general, finding optimal solution for NP-hard problem is computationally difficult in the general case. So we need to diverse effective heuristic methods to find good suboptimal solutions. For this, data mining or learning techniques, once again, in the broader sense, can be used to provide useful tools. These methods can be used, for example, to better understand the structure of the search space, can help us to discover patterns of high quality solutions and exploit these patterns, can make also right decisions during the search space, during the search process, can be also used to learn informative evaluation function and so on. So today I will focus on the first 2 points. Okay. So I will now begin to present the first case study, which is about the probability learning, where we will use reinforcement learning as a tool to solve the class of grouping problem. Okay. So a grouping problem. So given a set of n items, a grouping problem is just to partition these items into k different groups. So just as we already seen previously for the coloring problem. In these problems, this value k can be fixed, like in the k coloring problem, or can vary. Okay, so for example, for problem with fixed k groups, we have the graph k coloring problem. We have also graph k-way partitioning problem. And for problem with variable groups, we have the general coloring problem and a number of variants, so like sum coloring, also bin packing and clustering and so on. So in this large class of grouping problem, we may have several situations, in particular with k fixed or not. Of course, when we do a grouping problem, there are specific constraints and there are specific optimization objectives, of course. So in some cases, the grouping name may be relevant, or the grouping may be irrelevant, like we say for, previously for the k-graph coloring problem. Okay, so the probability learning approach I will show you is based on a very simple idea. So we will use a probability matrix, like you see here. So we have n items to be partitioned, to be grouped in k groups. Okay, so we will create a probability matrix like this, where each value, so each value is just the probability that is the ith item selects the GS group. So each line, each line in the matrix is a probability vector. So in this vector, we have the probability of this item belong to a particular group. So to start with, we have no knowledge about the probability. So we will just initialize this matrix with equal probability 1 over k. So this we will use this probability to do our the grouping task. Okay, and then we will learn information from new solutions, and we will use this learned information to update the matrix. Okay, those matrix will be used to create new solutions. Okay, so the basic procedure, so the general procedure is summarized here. So the general procedure is quite simple. So we start with initial probability matrix as just as I explained before. So using this probability matrix, we will create a solution. So we will use this probability, and we will obtain a grouping. So of a solution, a first solution that we call ST. Okay. So this solution will be improved by optimization methods. Here we will use a sample methods, so it's a local search methods, so a descent-based local search methods. Here, of course, we can also replace this method by any black box optimization methods. So the purpose is to improve the quality of the initial solution to obtain an improved solution, ST hat. Okay, so now we have two solutions. We have the initial solution, which is obtained by applying the probability matrix, and the improved solution, okay, obtained by this optimization methods. And now we will compare these two solutions to say which items have moved from its group to a new group. Okay, so we will compare these two solutions to say which are the groups that have moved their place from their current from their group in ST to a new group in ST hat. So this comparison will give a feedback signal that we will use to do a kind of reinforcement learning. We will use this information to update the probability matrix. So from this new matrix, we will create again a new solution, and we do the next iteration. So this method is, the general procedure. So it's a very simple. So this in the general procedure, we have several parts. So the probability matrix, using this probability matrix, we must find a way to create a new solution from this probability matrix. And then we need optimization methods to improve an improved solution. And we need a reinforcement learning technique to learn information that will be used to update the probability matrix. So
excuse me, Gene.
Yeah.
I'm sorry. This is Vincenzo Cotello.
Okay. Hi.
I just have a quick question.
Yeah.
Since we're dealing with probability values, if I understood correctly, you just create the grouping using the probability only once, right?
Yes.
Just using that probability distribution and creating a solution, and then you optimize.
Yes.
Would it be more, let's just say, efficient to instead create a set of solutions using the probability at any instant, not only at the beginning, but even in future, updating of the probability distributions. And from the small set, that will, in a way, represent better the effect of the probability values, because the way you're using them seems like like a deterministic process, when instead it's a randomized process.
Yes.
So you should use, I don't know, K or M solutions given the probability values, and then optimize the M solutions.
Very nice comment. Very nice comment. Really very nice comment. In fact, in whatever show, so very nice comment that give me. In what I will present here, we will use the probability to generate only one solution at each iteration. You are absolutely right. We may use the probability to generate many solutions. This approach would be probably more robust, but we didn't test this yet. We didn't test it, but the idea is very nice, I think. The idea is very nice. Okay, in fact, when we create a new solution, there are several ways to do this. Okay, so we have tested several strategies. For example, we can create a solution um, with a greedy selection. So if we do this, we have a deterministic methods to build a new solution. We can also use these probabilities with the ruled Euler selection. So in this case, it's a stochastic methods. So we give a more chance for a group for an item when the probability is high. So we have also tested a hybrid selection. So with a NOS probability, we can select randomly, and with one minus this probability, we apply as a greedy. So there are many ways to generate a grouping according to the probability matrix. Once again, the comments is very, very relevant. Indeed, we can, at this level, we can generate several solutions instead of only one solution. So it's a possibility that we can test in the future, of course. Okay, so in our case, so according to these strategies, it seems that the hybrid selection performs the best. So we will use these methods. So once we have our solution, we will now apply optimization methods. As I said before, we can use any optimization methods. So in our case, we have used a very simple method, so step-by-step descent, local search, and also we have also tested a taboo search. Okay, so now when we do the updating of the probability methods, there are some formulas, so it's not necessary to read these formulas. So just to have a look of the ideas. So the basic ideas is very simple. So it's based on the idea of reinforcement learning. So if for a item, if this item doesn't change its place, so it's stay in the same group between the starting solution and the improved solution. In this case, we will reward its group. Okay, so we will increase the probability. And instead, if an item moves from its original group to a new group, in this case, we will penalize the discarded group. Okay, we will at the same time we will compensate the new group. So we will use these formulas to update the probability matrix. Okay, from time to time we will also apply a probability smoothing to reduce the probability to forget some old decisions. So we apply this to our coloring problem. So in the coloring problem, as I said before, is the CSP problem. It's not really a optimization problem. In our case, we will consider this problem as an optimization problem. In fact, we will given a color to each node, even if there may have some conflicts. For example, in our example here, this is the coloring. This is not a legal coloring because we have two conflicts here. So a conflict is an edge whose endpoint receiving the same color. So there we have two edge, we have two conflicts. So the purpose, so here we have an artificial optimization objective, which is the number of conflicts that we want to minimize. So if this number comes to zero, so zero conflicts, in this case, we obtain a legal coloring, a legal solution. So we will consider this K coloring problem and this minimization problem. To solve this problem, we will use a taboo search methods. Okay, so I will not go to detail to this taboo search coloring problem. Is quite standard, quite simple. So during the taboo search, we will just change the color of a conflicting vertex. Okay, for example, in our case, we have three 3 nodes, they are in conflicts. So at each iteration, the double algorithm will choose one node and change its color. So for example, in our case, if we change the color of this node C, we will probably obtain a Lego coloring. Okay, so this is the basic idea of the double coloring algorithm. Of course, we will use also a double list to forbid the vertex to receive the old color. Okay, so this is a technical detail. So applying these methods, I mean, double call with the probability learning technique, we obtain this algorithm. So we have performed our, of course, tests on Dymax graphs. We have compared this. If we compare the results of these methods with some popular methods on graph coloring, including local search methods, 3 representative methods, and a number of population-based methods. They are here. In fact, for graph coloring, the most powerful methods are population-based. In fact, in all these methods, they use a crossover and tuple call in the most cases. Okay, so if we check the results, I will not go to detail to explain every result, but just to say that globally, this method probability learning-based methods is performs better than all local search methods. Even it's rather simple. Okay, even it's rather simple because the coloring algorithm is basically a double call algorithm. Okay, so even with this rather simple coloring algorithm compared with the probability learning component, this algorithm can compete well with most of these rather complicated population-based algorithm. Okay, so that's show the interest, the benefits of using the probability learning mechanism compared with optimization methods. Okay, so this is what I want to show you for this probability learning-based methods. Okay, now I move to a second topic. This is a research topic concerning rather fundamental issues. So if we check the literature in combinatorial optimization, in fact, most methods works like a black box methods in the sense that we are given a combinatorial search space. We don't really know. We have no knowledge. We know nothing about this search space. So, for example, if you take a local search methods, so the local search method just navigate in the search space by using a neighborhood guided by the evaluation function. So there's it's a kind of black box optimization. Why we do this? Because there's no much methods, well-established methods that allows us to understand, to make a search space understandable. So in most cases, we do black box optimization. So that in the most favorable case, we would like to have a white box, but this is impossible in practice. So at the trade-off between black box and a white optimization, we can think about gray box optimization. So in what I will show you is kind of gray box optimization in the sense that we will try to obtain some information about the search space, and once we got this information, we can exploit this information during the search space. Of course, we may have several ways to do this. In our case, we will use a data mining technique. So it's an existing technique to to analyze the spatial distribution of local optimum in a given search space. Okay, so if we so this is these are some interesting questions we want to answer. So what is the spatial distribution of local or global optimum given a search process like a local search methods? So how does its trajectory looks like? Okay, so which are the regions the process is more likely to explore, and so on. So in this part of the talk, I will give some answers to the questions. Okay, so the methods we apply is based on a distance matrix to capture the proximity among the local optimum solutions. Okay, so we will do this for the graph k-coloring problem. So as I explained before, a coloring is just a partition of the nodes into k groups. So now, given two coloring, given two groups, we can define their distance. So the distance is what we call the partition distance, which is just the minimum number of the elements that need to change their class so as to transform one solution to another solution. Okay, so we have an example here. We have two solutions, so there are two coloring, if you like. We have three classes, so ABC, or so red, yellow, okay, something like this. So ABC, and we given these two solutions, two coloring, their distance is 2 because we can just move two nodes from one solution to obtain the second solution. For example, from S we can obtain P by moving 8, by moving node 8. Okay, and then by moving 8 here, and by moving 5 here. So we can obtain S from P. You can do also in another from S to P. So in any case, we are just to need two nodes to transform one solution to another solution. So the distance is 2. Okay, so this distance can be calculated by the Hungarian algorithm. Okay, so we will use this distance matrix to measure the similarity between two solutions, two coloring, if you like. So to do this, we will use a tool, a very popular tool called MDS, so multidimensional scaling. So it's a data mining tool that can be used to visualize the level of similarity of high dimensional elements in a lower space. When I say lower dimension, that typically is in 2D and 3D space. So to do this, these methods provide a way to project n dimensional space onto 2D and 3D space. So from this we can visualize. Okay, we can visualize. Okay, so the Euclidean distance between the 3D point, projected point, will be an approximation of the real distance between the associated point, between associated coloring. So this tool, this data mining tool, give us a way to visualize the proximity between solutions in a large search space. Okay, so let me show you an example. So here, okay, before show you the result, I ask you a question. So according to your understanding, so given a search space, so how the solutions, in particular, how the high quality of local optimum solutions are distributed in the search space. Okay, I don't know if you have any idea about this. For example, do you think they are scattered everywhere randomly in the search space, or they are grouped or in some way or whatever? Okay, yeah. In fact, according to our study, these high quality local optimum solutions are not distributed randomly like this in the search space. They are in fact grouped. They are in fact grouped in small in groups in what we call spheres of small diameter. So concretely here, I will show you an example. So we have a group. So here is a graph, is a random graph. Okay, so we have we use 27 colors to color this graph. Okay, so we use coloring algorithm. So any graph coloring algorithm, which may be tuple search algorithm or population-based algorithm. So any coloring algorithm will be fine. So we use the coloring algorithm to obtain 350 best local optimum solutions, so high quality solutions. And we will plot, I will use the tool MSD to project these solutions in a 2-day space, in a 3-day space, as you see here. So now we have a direct visualization of these solutions. So all these points are solutions. As we may observe here, as we may see here, these solutions are grouped. You have a group here, a group here, and a group here, and some small group here. So most of these high quality solutions are grouped together. Okay, they are grouped together and they are covered by spheres of small diameter. So this is a knowledge. This is a knowledge. So we now have this knowledge. We know that in our search space, high quality solutions are probably very likely, grouped like this. So with this knowledge, if you have a search algorithm, what we should do, what the algorithm should do. So to answer this question, in relation with we just said about this knowledge, so we know that now if you found a high quality solution, it's highly likely that around this solution, there are other high quality solutions. So when you found a new high quality solution, when your algorithm found a new high quality solution, it's necessary to stay here to do intensified search, not go fast, do an intensified search in this area. And only after you have exhaustively explored this area, you leave. Okay, now if you found a new solution, high quality solution, once again, don't leave this area rapidly. So stay here to do an exhaustive search before leaving. So this is the idea that we will develop, we used and to develop an informed distance guided local search algorithm for graph coloring. So here we have used this knowledge to develop 2 procedures based on tuple search. So the first one is purpose is to do a diversified search, that is to find new high quality solutions sufficiently distanced. Okay, and another one, tuple search intensified. This is a tuple search algorithm which is responsible for intensified tuple search within each sphere. Okay, so here just to give you some idea. So we have our tuple search diversified. So we will use this algorithm to find new solutions, and we will memorize these new solutions somewhere. Okay, so this each recorded solution represent a different sphere. Okay, so we will record these spheres. We will a limited number of spheres. Each sphere represent, in fact, a new region where there may have other high quality solutions. Okay, so this is the purpose of the first algorithm, tuple search diversified. Okay, so I will move on to, so from the recorded spheres, we will now, for within each sphere, we will use our second tuple search procedure, so the TS intensified, to do a very intensified search within each recorded sphere. Okay, so to do this, we are given a sphere here. Okay, so the point one is the sphere center. So this is the recorded solution, and from this point we will use TS intensified to make a very intensified search in the sphere. So from this point we will search everywhere in this sphere. Okay, we will search everywhere until we believe that this sphere is entirely searched. There will be no more high quality solution in this sphere. Only at this point, we will leave this sphere to move to a new sphere. So that this sphere is also recorded. So we move to the second sphere, and we will do this. Okay, so this is the basic idea. We use MDS, so a data mining visualization tool, to obtain knowledge about our search space. Now our search space is kind of gray box. We will use this knowledge to design our search procedures. And with this strategy, we have obtained some very interesting results. In fact, when this work was published, so some time ago, this procedure, once again, this procedure is not very complicated in the sense that we use the tuple search, so they're local search-based methods. There's no population and no other complicated strategies. So using this knowledge integrated with tuple search, this algorithm has obtained one record result. For example, for this very hard benchmark. So this algorithm has obtained one coloring with one color less. So from 2024 colors to 223 colors. Of course, this result has been improved since then by other methods. Okay, so let's move on to the last talk. Yeah, in fact, this space cartography analysis has also other applications. So we can use it. We have applied this to create multiple parent graph coloring crossover operator. We also use this to ensure a sufficient diversity in the population algorithm and so on. So this knowledge has other applications as well. Okay, now let's move to the last case study, which is about application of another machine learning technique. I mean, a data mining technique to do optimizations. I mean, to be used in combination with optimization methods. So as you know, probably this concept of frequent pattern has been introduced for market basket analysis. In this case, we are given a transaction database. Okay, we have a number of transactions, T1, T2, and Tn, and each transaction is composed of a set of items. So, for example, the article we buy in a supermarket. Okay, so a subset of articles, a subset of items is called a frequent pattern if the article of this subset occurs frequently in the transaction database, no lower than a threshold. So the concept is very simple. So we will use this notion to apply this concept in the context of optimization. Okay. So the basic idea of a frequent pattern is related to a well-known concept in optimization is called a backbone. So the notion of backbone is known in optimization in different contexts. For example, in the context of the TSP, the traveling salesman problem, is known knowledge that given a set of high quality TSP solution, then there are always some short tool that are shared in this high quality tool. So this shared subtools is kind of backbone. That is, this short subtool generally is part of the optimal tool. So the frequent pattern is tightly related to this notion of backbone. Okay, so here, if we make a parallel between transaction and a solution space, we can say that a transaction is just a sample solution in the search space. So we have a solution, we have a transaction. So an item is just a solution attributes. For example, this may be a pair, so a variable with the value. So a frequent pattern is just a set of shared attributes in some high quality solutions, okay, which forms the kernel of optimal or high quality solution, just as I explained for the high quality subtool in the TSP problem. So in this methods, in the method we proposed, which we call frequent pattern-based search, we have several main components. So we have a solution optimization procedure. So this, once again, just like the first case study, we need optimization methods to do optimization to improve the quality of an input solution. Okay, we need also to transform a solution to a set of items. So just like we explained here. Okay, of course, we need also a methods to find frequent patterns. This can be done with some existing methods, as I will show you later. Once we have our frequent patterns, we need to select some frequent patterns, and from them, we will build new solutions. Okay, so we will have a selection strategy to do this. And from the selected frequent pattern, we will build a new solution. So we need also methods, a strategy to build a solution from the selected pattern. In fact, a selected pattern is a partial solution. You can consider a frequent pattern as a partial solution. So to obtain a whole solution from this partial solution, we need some strategy to do this. Okay, so the general procedure of the frequency pattern search methods is once again rather simple. Okay, so we began with initial population of solutions. So we use any optimization methods to obtain an initial set of high quality solutions. Okay, so this set of solution will be used to do data mining. So we will use this set of high quality solutions. We will apply a data mining algorithm, a procedure, to obtain a set of high frequent items, frequent patterns. Okay, from the identified frequent patterns, we will select one pattern that we call PP, and we will use this pattern to build a new solution. And this solution will be improved by our optimization procedure. So we will do this. Okay, so once the solution is improved, we will use this solution to update the set of high quality solutions we obtained here. Okay, so we will just do this. Let's just do this. From time to time, we will also, for example, when the set of high quality solution are sufficiently changed, we will rerun, we will reapply the frequency pattern methods to mine new frequent patterns. Okay, so we will just repeat this process to find the best solution possible, the best possible solution during the search. Okay, so how to construct, how to build the solution, a solution from mined patterns. So we will select, first select a pattern and create a solution. So to select a pattern among the identified frequent patterns, there are several strategies. So you can do this randomly. You can apply a greedy selection. For example, take the best one. For example, take the largest one. You can also use a tournament selection and so on. So there are a number of strategies that we can apply for pattern selection. Once a pattern is identified, is selected, we can complete this solution. So see the kind of backbone. Okay, so we will complete this partial solution either with random completion, critical completion, or guided by other AD solution and whatever. So we just need a strategy to build a full solution from a partial solution. Okay, and then we need optimization methods. So once again, any optimization method can be applied. This is just a black box component. So to improve the input solution that we obtained here. Okay, and this gives us an improved solution. So this optimization procedure, of course, ensures the key rule of search intensification. So now apply these search methods to the quadratic assignment problem. So we have already defined the problem before. So here we will just transform a solution into a set of pairs. Okay, so a solution for the quadratic assignment problem is just a permutation because we want to allocate, assign facilities, n facilities to n locations. So this can be easily represented by a n permutation. Okay, so we given a solution, given a permutation, for example, like this, we will just transform this solution into a collection of a set of pairs like this. So here we have a location and the facility. Okay, so here, so the facility 5 is located in location 1 and so on. Okay, so here we have this kind of very simple transformation. And once we have obtained this form of transformation, we can apply a mining algorithm. So in our case, we have used the very popular FP max star algorithm. So this is a very known data mining algorithm to mine, to identify frequent patterns. Okay, so now for the local optimization, for the optimization procedure, we just used existing algorithm called BLS. So it's the breakout local search. It's an old algorithm, but it's among the most competitive QP algorithm. So this algorithm is just a local search, a steepest descent local search algorithm compared with a particular perturbation techniques. So it's use three kind of diversification strategies. So directed or undirected or adaptive perturbation strategies to modify the best local optimum we found at each round of the search. Okay, so what's the conclusion? So in this case, we compare this frequency pattern-based search with some state-of-art algorithm. Among these algorithms, there are some parallel algorithm too. So I will not bother you with all these numbers. So just to say that compared to the BLS algorithm, which is one component of this approach, so the frequency pattern-based methods obtain better results in terms of the best percentage deviation. That is, in terms of quality, we obtain this frequency pattern search-based methods obtain better results. Also, in terms of computational efficiency, frequency pattern-based search is more computationally efficient. So with less computing time, we reach the same or better results. Now, if we compare with other reference algorithm, including three parallel algorithm, this algorithm is the second best in terms of the solution quality, and is the most effective in terms of computation time. So in this table, if you check this column, is the average percentage deviation from the best known results. So this frequency frequent pattern search has the second best value here, and the best one is here. Okay, so this is what I want to present today, and so I want to insist that most of the presented techniques, even if I presented them with a particular problem with graph coloring, with quadratic assignment, in fact, these methods are general enough to be applied to other optimization problems. Also, we can say that data mining and learning can boost existing optimization methods and can help create new methods too. Of course, there are still much to be done and explored. So to finish, I like to say also some words about the current study on using machine learning techniques to optimization, because if we check the literature in recent years in the area of OR, operation research, or in computer science, there are many papers where we will use machine learning methods to solve combinatorial optimization problems. Typically, we use a learning method directly. In fact, we will consider optimization methods as a learning task, and then we use directly a learning technique, so deep learning methods or whatever to handle the optimization problem. This approach is what we can end-to-end approach. The observation that I have, that you can have also, is that even if there are many studies of this kind, for example, people have applied this end-to-end approach to popular problem like TSP, like coloring, like SAT, and so on. And I didn't see yet convincing computational results in the sense that very often they are applied to small size problems, and their results, they don't compare directly with the best results for the problem in the literature. So it's I didn't see yet convincing results in this sense. So what I want to say is that maybe one, of course, there's still much to be done, much to be explored. But in my sense, I think one of the most promising idea direction would be to combine to hybrid, to combine learning methods in the broader sense, in the large sense, with optimization. Not only consider an optimization problem as a learning task, but in our optimization methods, each time we have a decision to take, we can consider use some learning techniques. Once again, here when I talk about learning, it's not necessarily deep learning. It's not necessarily complex neural networks. Learning may be any learning methods that are the most suitable for your decision task. So according to the decision you want to make, according to the to whether you want to do a prediction or to make a choice during the search procedure, we may apply different learning techniques. So in my sense, combine learning with optimization is definitely a good idea, but we need to find the best way to combine them. So that's all I want to say. Okay, thank you for your attention.
Okay, thank you very much, Jinkao, for your very interesting and inspiring talk. So, someone want to? There is a question.
Yeah, I have. So I show you also some papers here. So if you, so I said every time. So since my English is not very good, so maybe it's not very easy for you to follow me. So if you want to have more information, you can also check these papers after the lecture.
Okay, I see Yun Kufeng, please.
Yeah, can you hear me?
Yeah, I can hear you. Okay.
Yeah, I was a little curious about your case 2. You used taboo search, right? In the previous slides.
Yeah.
Yeah, I would even just around 20 the page the 20 about previous more previous, I mean. Yeah, here.
Okay, so.
Yeah, I was a little bit worried about how good do you define to escape or to escape the local minima. Yeah, because I see you find that there are some optimal solutions. They group.
Yeah. Okay. So here, for this graph, and the optimal, the chromatic number. So the optimal number of colors is 28. Okay. So we use one color less in order to have conflicts, because as I explained before, we tackle the key coloring problem as a minimization problem, where we want to minimize the number of conflicts. Okay, so we use 27 colors. In this case, we are certain that any solution will have a number of such a number of conflicts, right? Okay, so we just fix a threshold for the number of conflicts. So fewer than this number is a high quality solution. For example, if we know that with 27 colors, the best solution we can find has 3 conflicts, then we will collect solutions with, for example, with 5 conflicts, with 10 conflicts, but not with 20 conflicts. Is it clear or not? So we just collect solutions that a little bit worse than the best solution we can find. We will qualify these solutions high quality solutions.
Yeah, I got it.
Yeah,
thank you, Leon.
Okay, no problem.
Okay, thank you very much for the question. Other question?
Can I make a simple observation?
Yeah, go ahead.
In my experience, many of the problems in combinatorial optimization problems, especially when dealing with graphs, are basically, you mentioned something in one of the previous slides, basically a problem of finding the best permutation of in case of graphs, the best permutation of the vertices of the graph.
Yeah.
Even for coloring, if you have the optimal permutation would be that first you find in the permutation all the vertices in the first group, then all the vertices in the second group, and so on. So it would be interesting to come up with a learning mechanism that will allow us to judge how good. Judging actually how good the permutation is the consequence for the optimization problem. But it would be interesting to find a general mechanism to learn from the permutation of the objects in play that we've seen in the previous attempt, so that we could quickly find better solutions in the next attempt. I don't know if I made myself clear. So I don't know if you ever thought of it in terms of let's look for the best permutation and let's try to learn the characteristics, the features of good permutations.
Yeah, I think once again the comments, your comments are very interesting. Yeah, indeed, there are many graph labeling problem like bandwidth minimization and so on. All these problems are a permutation problem. And so when we want to learn features, I think we should consider the constraints of the problem, but also the optimization objective. So personally, I don't think it's possible to have a very general learning strategy that can be used to learn everything from from a given set of fixed features or attributes without considering specific constraints and specific optimization objectives. So in the best, I suspect that we need to have a very deep understanding of the given problem in terms of constraints, in terms of the optimization objectives, and only from this it would be possible to apply some meaningful learning techniques. So for example, for the graph coloring problem, of course, this graph coloring problem is not naturally a permutation problem, but it's it's a grouping problem. So for this problem, So the first study, I mean, the first study is many in the past, when people working on this problem, typically we consider only this problem as a assignment problem, in the sense that we want to assign colors to nodes. Okay, of course, this is the initial definition of the problem, assign colors to the nodes. But in terms of problem constraint, this interpretation, this definition is not really interesting. In fact, for the graph coloring problem, what is really important is not assign colors to nodes. What is really important is that which nodes, which vertex, which nodes can be put, can reserve, can have the same color, which nodes can stay together, in a group. So this is a understanding. This is a understanding of the problem. Without this understanding, we cannot design sufficient search search operators. So it's also based on this standing, specific crossover for the graph coloring has been proposed. So which will use this this understanding of the problem to transmit large group of nodes from parent solutions to offspring solutions. So so I don't know.
Okay. Okay. Thank you.
Thank you.
Okay. Thank you. So other questions? Okay. Since no, so we are 1 hour and a half. So Jean, thank you very much for your interesting talk. I hope to see you very soon to visit us in Catania when it is possible. And thank you very much to everyone for attending this seminar. Thank you.
Okay,
Bye-bye.
thank you. Yeah, okay, thank you. Bye-bye.
Thank you, bye.
Thank you, bye.
Thank you, bye
Thank
bye.
you. Thank you, bye-bye.
Bye bye.
Thank you so much.
Ciao, Andrea.
Thank
Ciao
you.
Mario, ciao,
Ciao.
bye bye.
Goodbye.
Bye. Bye, Adia.
Thank you, bye.
Tutto ok?
Sì, tu?
Tutto bene. Lì com'è il tempo? Hey, Taimi, how are you?
I'm fine, and you?
Yeah, fine.
Thank you for this course.
Yeah, thank you too for your attending.
Yes.
And see you soon. Ok. Andrea, perciò tutto bene? Lì com'è il tempo?
Adesso oggi piovigina avanza, tutto bene, dai, tu tranquillo. Tu come va?
Ma tutto bene. Il tempo è carino. Ha fatto 2 settimane fa, credo, una pioggia inaspettata. Però adesso si è ripreso. Ci siamo abituati a forte piogge, quindi c'è stato veramente tutto allagato.
No, no, niente, no, qui a Udine è tutto tranquillo. Quindi bene, dai.
Va bene.
E niente, dai, noi tutto tranquillo, tutto a posto, sai, si lavora, si fanno i corsi, io ho i compitini qua da correggere, ho i compitini fatti stamattina da correggere, i parziali, come li chiami, fatti stamattina.
Tu c'hai il semestre carico, questo?
Questo c'ha 2 corsi, sì, poi il prossimo invece c'è un corso più avanzato, quello di scheduling, quindi meno studenti e insomma, più facile da gestire. Invece questo qui c'ha 2 corsi più di base. Quindi...
No, io c'ho il contrario, il primo semestre è un po' più leggero, il secondo semestre piuttosto è più pesantuccio.
Bene, dai.
Va bene, ci vediamo presto allora.
Dai, non so, speriamo di trovare qualche occasione, dai, vedersi.
Infatti, cercheremo qualche occasione di vederci. Se c'è
Ciao.
occasione di trovare a Udine.
Guarda, se vuoi venire a un seminario, insomma, qualcosa lo organizziamo, senza problemi, volentieri.
Con piacere. Vediamo appena finisce questo semestre se riesco a organizzarmi.
Va bene, dai, ci sentiamo volentieri.
Ok. Grazie Andrea di
Ciao,
tutto.
grazie a te, ciao, ciao,
Ciao.
grazie del seminario, ciao, ciao, dell'organizzato, ciao.
Ciao. Devo disattivare la registrazione.